So in section 3, we are going to take a look at logarithms. So a logarithm is the inverse of an exponential equation. So it's used to solve for time, which is our exponent in an exponential equation. So when you think about what is a logarithm, it's the answer to the question, how many of one number multiplied together are needed to make another number. It solves for an exponent if it's not obvious already. So there's 3 different forms you can see for a logarithm. So the first one is a base 10 logarithm, which is what's known as the common log. So anytime you see the log button on your calculator, it refers to the common log. So that's log of A equals X. So our base is unwritten because it's assumed to be a 10. Okay. Now, most of the problems we're going to deal with are going to have either base N or base E, which in that case, it's called the natural log. So anytime you have a base N, so it's any number, it's written in the form log base B of A equals X. So your base number B can be any number. Obviously, it has to be positive, just like in an exponential function, it has to be a positive. Then we have the natural log. So that's ln of A equals X. So that base is E. So when we have our continuously compounded interest, when we convert it to logarithmic form, when we go to solve for our exponent, because the base of a continuously compounded interest formula is E, instead of using log, we use natural log because the base is already E. So how are we going to use logarithms to solve? So we have to know how to switch forms. So we have to know how to go between exponential and logarithmic form, and vice versa. It works in both directions. Now, none of the problems we're really going to do are going to require us to go from logarithmic to exponential form, but we will need to know how to go from exponential form to logarithmic. So we're working off of the idea that exponential form is A equals B to the X. Okay, so you have some base number raised to an exponent equal to some other number A. So if I'm converting that to logarithmic form, I have log. The base of the exponential equation becomes the base of my logarithm of my A, whatever my value A is, equals X. And it works for the same way for the natural log. So that would be A equals E to the X. And when I convert that to the natural log, it's just going to be natural log of A equals X, because the base is already an E, so I don't need to write it. So we're going to do some examples where we take an already set up exponential equation and we're going to convert them to logarithmic form to help us solve for the exponent X. So in every case when you're converting to logarithmic form, the only thing that needs to be on that right side or with the exponent is your base number. So if there's a number being multiplied in front, you have to get rid of it first. So 49 equals 7 times 10 to the X. If I want to solve for X here, the first thing I have to do is divide both sides by 7. So 49 divided by 7 is 7. So we get 7 equals 10 to the X. Now this is a common log. My base of my exponential equation is 10. So when I convert it to logarithmic form, I don't have to write the base 10. It's going to be log of 7 equals X. And we're not going to solve these right now. We'll do that in a second But for right now, we're just writing them in logarithmic form. So our second example, 64 equals 16 times 3 to the 2x. So my first step is going to divide by 16. So we get 4 equals 3 to the 2x. So when I'm converting to logarithmic form, my base is going to be 3. I'm going to do of 4 equals my exponent 2x. Next we have 148 equals 4 times 5 to the x over 9. So my first step is going to be divide both sides by 4. We get 37 equals 5 to the x over 9. So I'm going to convert it to logarithmic form. I have log base 5 of 37 equals x over 9. Our last example, 693 equals 9e to the 12x. So again, first thing I'm going to do is divide by 9. We get 77 equals e to the 12x. I'm going to use natural log here, so it's going to be the natural log of 77 equals 12x. So the question now becomes, now that I have my exponential equation in logarithmic form, how do I finish solving for x? For our first and fourth examples, it's pretty straightforward. You'll evaluate in the calculator and then divide. But the second and third examples we looked at, the bases weren't the common base, for the common log base or the natural log base of 10 or e. So how do we evaluate that? So we're going to use something called a change of base. So it's used to evaluate a logarithm with a base of n. So any number that's not 10 or e. Okay, so any other base number as long as it's not a 10 or an e. So the change of base formula says if you have a log with base b and you're evaluating it with some number a, that's the same as doing log a divided by log b. So what we do is we take that logarithmic form that has a base other than 10 and we rewrite it with a base of 10 so that we can evaluate it in the calculator, because the calculator only works with base 10 or base e. So go ahead and take those examples that we just did and finish solving for x. So that first example, we had log 7 equals x. So this one's straightforward. It's just log. So you're going to find the log button on your calculator and you're just going to plug in 7. And we're going to get x is 0.85. Most of the time here when we're solving for x, we're going to get a decimal of some sort, which is fine. Our second example, we had log base 3 of 4 equals 2x. So we have to do two steps here. The first thing is we have to evaluate the log base 3 of 4 using our change of base formula. But then we also will have to divide by 2, because unlike our previous example where we're just equal to x, in this example we're equal to 2x. So the first thing I'm going to do is log 4 divided by log 3. So it's important here when you're plugging this into your calculator, you close the parenthesis after the 4. So you do log 4, close the parenthesis, divided by log 3. So we're going to get 1.26 equals 2x. And then the last step is to divide by 2. We're going to get x equals 0.63. We then had log base 5 of 37 equals x over 9. So again, my first step is to use my change of base formula. So log 37 over log 5. We're going to get 2.24 equals x over 9. Now in this case, I'm not going to divide to get x by itself. I'm going to multiply. So I'm going to multiply both sides by 9. And we're going to get x equals 20.19. So far, we've been dealing with log. But our last example had that base e. So we had natural log of 77 equals equals 12x. So there is a natural log button on your calculators. It's ln. It's typically very close to the log button. It's usually directly below it or to the left or right. So you'll find the ln button. You'll put in 77. We get 4.34 equals 12x. Then we'll divide by 12. And we get x equals 0.36. So the examples we've been doing were just general, regular exponential equations. But most of the problems that we're going to be dealing with are word problems, similar to when we were looking at the problems from section 2. So we're dealing with percent increase or decrease, our half-life, doubling time, compound interest, and continuously compounded interest. So what we're going to do now is we're going to look at the examples we originally had in section 2, and instead of solving for a future value, we are going to solve for the amount of time it will take to reach a specific value. So we have that the population of a certain animal species decreases at a rate of 3.5% per year. You have counted 80 of the animals in the habitat you are studying. We're going to write a function that models this, and then we're going to determine how long it will take for the animal population to reach 15. So our equation that we had that modeled this was y equals 80 times 0.965 to the x. That was our equation. So now we want to know how long will it take for the animal population to reach 15. So I'm going to be plugging in 15 for y. So we're going to have 15 equals 80 times 0.965 to the x. And now it's just like those examples that we did before. I'm going to divide both sides by 80. We're going to get 0.1875 equals 0.965 to the x. Now we're going to convert it to logarithmic form. So it's be log, my base is 0.965 of 0.1875 equals x. And now I just need to do my change of base. So we'll do log 0.1875 over log 0.965. Again, make sure you close your parentheses after the 0.1875 before you divide by the log of 0.965. And we're going to get that x equals 46.99 years. So just like when we did the examples where we plugged in a value for x and we had to have units on our final answer, we have to have units on our final answer here. And because we are typically solving for time, our units are going to be whatever measurement of time the problem gives us. So we were given information about population growth per year. It could be days, months, hours, weeks. It really just depends on the problem. The second example we looked at was the world population in 2000 was approximately 6.08 billion. And assuming that the annual rate of increase stayed about 1.26%, we wrote an equation. And now we're going to figure out in what year will the world population reach 10 billion. So our equation here was y equals 6.08, 1.0126 to the x. So now I'm going to be plugging in 10 for y. So we'll have 10 equals 6.08 times 1.0126 to the x. We'll divide by 6.08. Okay. So we do not get a nice decimal here. So anytime you don't get a nice decimal, I prefer at this point in the problem, you go at least 3 decimal places. So this is going to be 0.645. We don't want to round too much too early. Because if we round to only 1 or 2 decimal places this early in the problem, our answer could be very off. So I want to use at least 3 decimal places here. So we get 1.645 equals the 1.0126 to the x. Converting it to logarithmic form, we have our base of 1.0126. Inside our logarithm is 1.645 equals x. Use change of base. Now, the important thing to remember here is when I get an answer, it will be the number of years. So x equals 39.8, which is roughly 40 years. So this is the number of years since 2000. So my final answer is not going to be 40 years because it doesn't ask us how long until the world population reaches 10 billion. It asks us in what year will the world population reach 10 billion. So 40 years after 2000, so it's going to happen in the year 2040. And it will be very interesting to see, since that hasn't happened yet, if it does take until 2040 for our population to reach 10 billion. So next we have, I did slightly change this problem. So a new truck that sells for $30,000 depreciates 12% each year. We'll change our function slightly and then figure out how many years it will take for the truck to reach a value of $18,000. So accounting for my slight change in the truck, we're going to have y equals 30,000 times 0.88 to the x. We want to know how many years it will take for the truck to reach 18,000. So we'll have 18,000 equals 30,000 times 0.88 to the x. We're going to divide by 30,000. We're going to get 0.6 equals 0.88 to the x. Converting to logarithmic form, we'll have log base 0.88 of 0.6 equals x, which then becomes log 0.6 divided by log 0.88. And we'll get that x equals, now in this case we get 3.996, which I can round up to 4 years. This is the only acceptable type of problem where I will accept a whole number, because typically speaking, we always round 2 decimal places. So if I wanted to round 2 decimal places here, the 6 would make that second 9 round up, which would make the 9 in front of it round up, which would give us a whole number of 4 years. Both 3.996 and 4 are acceptable correct answers for this problem. So those were the 3 examples we did over general exponential growth with a % increase or a % decrease. Next, we're going to look at example of half-life. So our half-life example previously was that arsenic 74 has a half-life of 17.5 days, and we have an initial amount of 90 milligrams, and in this problem, we're going to solve for the amount of time it takes it to reach 15 milligrams. So we'll have our equation was A equals 90 times 1/2 T over 17.5. So we'll have 15 equals 90 times 1/2 to the T over 17.5. Divide by 90. Which is a nice fraction. It does simplify to the fraction 1/6. So if you can divide and leave it as a nice fraction, go for it. Our previous examples where we divided, not necessarily nice fractions, but 1/6, very nice fraction, I'm going to go with it. So then it's going to be log base 1/2 of 1/6 equals T over 17.5. Use our change of base formula. We'll do log of 1/6 divided by log of 1/2. And we get 2.58 equals T over 17.5. And our last step is to multiply both sides by 17.5. So we're going to get T equals 45.24. And in this case, our units are days. So for half-life, you want to make sure you're always using the units that's provided into your problem. So half-life can have any measurement of time: hours, minutes, days, years, months, whatever it may be. I did add 2 more examples that were different, that are addition to our section 2 notes. So I wanted to add an example of doubling, since it is something that you guys saw on the Delta Math, and it is something you'll see on our next Delta Math where we're solving for time. So we have that a certain bacteria doubles every 3 hours. And there are currently 250 bacteria in a petri dish, and we want to determine how long it will take for the bacteria to reach 900. So the doubling formula is the exact same as half-life, except the base is now 2. So our equation would be A equals 250, then in parentheses 2, T over 3. So the only difference between a half-life formula and the doubling formula is the base number goes from a 1/2 to a 2. So we'll have 900 equals 250 times 2 to the T over 3. We'll divide by 250. We'll get 3.6 equals 2 to the T over 3. Converting to a logarithm, we have log base 2 of 3.6 equals T over 3. Change of base becomes log 3.6 divided by log 2. So we'll get 1.85 equals T over 3. Then we multiply by 3. And we get T equals 5.54 hours. So the last three examples we're going to be looking at are going to be examples of solving for time using compound interest and continuously compounded interest. So I added a second example of compound interest because it is the most difficult equation to solve for time, mainly because that base in parentheses is that 1 plus r over n. And then that's what makes it difficult, is that base number. So we have our equation. It's going to be that we deposit $500 into an account yielding 1.5% interest compounded quarterly. We want to solve for how long it will take the account to reach $2,500. So we'll have 1 plus 0.015 over 4, and then our exponent will be 4t. I want to say the most common mistake I see with solving for time for compound interest is forgetting n with our exponent. A lot of people just put t there. You want to make sure you have n as well. So we'll have 2,500 equals 500. And then just to make life easy, I'm going to figure out what 1 plus 0.015 over 4 is. So we get 1.00375. It is extremely important that for compound interest examples, you put the entire decimal. Do not round. If I rounded, I can't use 1. That's the first thing. You cannot have a base of 1 for a logarithmic equation. Secondly, I don't want to put 1.004 because the answer I will get is very, very different. I'm not going to show you, but I can tell you that for any problems we do in the future, especially on Delta Math, if you don't use all of the decimal, you will get an answer that is very off. Now we can treat it just like all of our other examples. So we'll divide by 500. We get 5 equals 1.00375, the 4t. Whoops. Which becomes log base 1.00375 of 5 equals 4t. Change of base. We get 429.99 equals 4t, then divide by 4. So we'll get 107.5 years. So it'll take a very, very long time for this account to reach $2,500. Very, very sad. So the last two examples I changed slightly from the examples they were in section 2. So we're going to deposit $1,200 into an account yielding 3% interest compounded monthly, and we're going to determine how long it will take the account to reach $1,800. So accounting for my slight change, we'll have the equation A equals 1,800, 1 plus 0.03 over 12, and then our exponent, 12t. Oops, sorry. My initial amount is 1,200. Sorry. Okay. Now I'm going to plug in 1,800 for A. So I made the change here so that the 1 plus 0.03 over 12 would be a nicer decimal. So 1.0025. We're going to divide by 1,200. We're going to get 1.5 equals 1.0025 to the 12t. Converting to logarithmic form, we get log base 1.0025 of 5 equals 12t. Change of base. we're going to get 644.58 equals 12t. Then we're going to divide by 12. And we get 53.71 years. Remember, the only problems where time is only in years are going to be the compound interest and the continuously compounded interest. Doesn't matter how interest is compounded for the compound interest formula. So like the previous example, it was quarterly. This example was monthly. That does not affect the units. The units on the final answer are always going to be years. Okay. So it's going to be the same thing for number 8 when we look at a continuously compounded interest. So it's the same initial amount, same interest, but this time just continuously. So we'll have A equals 1200 E, and then our exponent would be 0.03t. And we're solving for how long it will take to reach 1800. So we'll have the 1800 equals 1200 e to the 0.03t. Going to divide by 1200. We still get 1.5 equals e to the 0.03t. But because our base is e, we're going to use natural log. So it'll be natural log 1.5 equals 0.03t. Which we can just evaluate using our calculator. So we'll get 0.41 equals 0.03t, and then we'll divide by 0.03. And we get that t is 13.52 years. And if we're comparing that to our compound interest, where interest was compounded monthly, this is going to take about 40 years less to reach 1800 than the compound interest formula. So unlike the example we looked at where we plugged in an amount of time and they were only about 20 cents off, or maybe it was 40, in this case, the amount of time it takes is significantly less for a much higher number. If you have any questions about logarithms, logarithmic form, converting from exponential to logarithmic form, change of base, any of the examples we did, please let me know.